we can have achieve better utilization multiple cores of processors. As you can see from the slide in the diagram, by using parallel streams, we can divide the code into multiple threads that are executed in parallel on separate cores. And the final result is a combination of individual outcomes. Well, but the order of execution, however, is not under our control. So therefore, it's advisable to use parallel streams in cases where no matter what is the order of execution, the result is unaffected and the state of one element does not affect the others. And to create parallel streams, we have two methods. So first, we can use parallel method on a stream, or we can use parallel stream on a collection. So let's check our demo on parallel streams. As you can see here is that main method, and here we have a list of integers, and its name is numbers. And here we are creating stream object, and we are using parallel method, and we are using terminal operation for each. And inside it, we are simply printing out it to console and passing it the current value and getting thread name. Let's try to run this demo. As you can see from the logs, here we have messages, logs, which we are getting by using parallel, and it's using parallel for join common pool workers, and we are here in getting the main points of a task. Let's move on. Well, in Java 8, to our JDK, they added a new package, Java Util concurrent package, and in this package, they added very useful and helpful concurrency classes and utilities for multi-threaded programs. They are executor services, safe collections, which are very optimized for concurrency and multi-threading, locking facilities, locking framework, which is very useful and very extensive in comparison to synchronized keyword. And also in concurrent atomic package, we have they added atomic wrappers for primitives and references. Well, when working with threads in Java, it's easier to use these concurrent utilities because it's really easy to use, and they are increased reliability because they are really better tested, and they are by using these utilities we can reduce programming effort. That's why, and also by using these utilities we can achieve more understandable code, more maintainable code, and in a conclusion, we have very convenient way working with threads in Java. Let's move on. Well, locks. Lock is a more flexible and sophisticated thread synchronization mechanism than the standard synchronized keyword. Lock API interface, provides more extensive operations for locking. Well, there are a few differences between synchronized keyword and locking API, lock API. Well, in synchronized keyword or a synchronized block is fully contained within the method. In lock API, we have a lock method and a lock and unlock method operation in separate methods. So it's very convenient to control locks and unlocks by using locks, lock API. And lock may be acquired with lock and later released with unlock methods wherever we want. Well, comparing to synchronized keyword, locks allow also specify wait timeout to write and more error-resilient programs. Also, synchronized block doesn't support fairness. That means any thread can acquire the lock unreleased. But by using lock API, we can specify the fairness property. It means that it makes sure that the longest waiting thread is given access to the lock. Let's move on to demo and check out the logs. Logs. Here you can see we have count thread, which implements runnable, and there we have common resource object, which is our class, and it's simple mockable object, which includes only one variable x. And we have reintent log. It's one of the implementations log API, which provides more extensible features, operations on log. You can enter in the log multiple times and it counts this log enters. And we have here constructor and we overrided run method, and in overrided run method we are logging it. In try block we are assigning 1. In for loop we are simply printing to console, and we are here we incrementing the x in our common resource and simply putting sleep to simulate long-running job. And in finally block, we are unlocking it. Well, let's look to main method. In main method, we are creating common resource object, and also we are creating locker by using reintent lock constructor. And in for loop, we are creating threads and passing them our created objects, and we starting it. Let's try to run it and to check the logs. As you can see, by using logs, we are getting thread 1 and 1, 2, 3 in a followed manner, and so on. And we have 5 threads because here in the main method we have maximum for 6, and the initial value is 1. And we have 4, the second value, yeah, because in our count thread we have maximum 5. Yeah, that's why we are getting it. For example, if we remove lock, we can check out the difference. Let's try. We remove logs, and what will be our result? As you can see, it's unpredictable result where thread 1 gets the resource and thread 5 gets the resource and thread 4, 3. It's very undesirable behavior of our code. Let's fix it and move on. Atomic. Well, as you know from chemistry, I think all we know them from chemistry, atom is a smallest unit of a matter which can be divided. It means that is the smallest unit, yeah. And the atomic operations are the smallest operations, and they cannot be divided by operation system schedule or schedule of GAM. Also, it's impossible to observe intermediate state during it. Well, for example, in Java, if you want to increment a variable, volatile or non-volatile, it doesn't matter. It takes 3 actions to increment it. First is reading variable, second one adding 1 to it, and then the last one is writing it back to memory. As you can see from the diagram in the slide, we have thread A, thread B, and we have integer 17. Both threads reads it, both threads increments it, and while in the between the incrementing process, they are both incrementing almost simultaneously. Yeah, and here we are losing the update. Instead of 19, we are getting 18. It means we are losing update. So to fix this kind of errors or errors, we can use atomic integer, atomic operations, and we can use in such case atomic operations. In Java, we can use atomic integer, atomic boolean, atomic long, and atomic references. Well, in Java, to make the variable atomic, we can use these atomic variables. Well, in Java, to achieve atomicity, they are used compare and swap algorithm to make these 3 actions into one. Let's move on to the next slide, and we'll talk about atomic integer in more detail. Atomic integer in overall holds a volatile and primitive, and it uses compare and swap netting instructions. Compare and swap is provided by many processor architectures. It allows an atomically set value of a field only if it equals some specified field. Let's look at the main methods of atomic integer. Well, to get the current value, we can use get method. And to set value, we can use set method without any condition. Well, to set with a condition, we can use method compare and set. We are passing expected value and new value, and atomically sets the value only if the current value equals to expected value. And also we have add and get method passing by delta, and we have an increment and get method which returns increments and returns the result value. Let's move on to demo to check it out. Safety atomic counter. Here we have counter, which extends from thread class. And here we have atomic integer type count variable, and we have a constructor, and we have a overrided run method. Inside this overrided method, we have max value 1 million. And in a loop, we are incrementing our atomic integer type counter. We are adding it and getting. Well, in the main method, we are creating an instance of our counter class. Also, we are creating 2 threads and passing it our counter class. We are starting it and we are joining because we need to wait for both threads to complete the execution and simply printing it to our console. Let's try to run it and to check it out. As you can see, 2 millions. Why 2 million? Because we have 2 threads, and we have a max value 1 million. If we want, for example, 3 million, we can add 1 more thread. Let's check the result. We added third thread, also passed our counter class. We started it and we call it join method to wait for both threads, all threads to complete. As you can see, we have 3 millions. Well, let's change it. For example, if we change it to int value, yeah, what happens? For example, 0. And here we can see we can use incrementation. As you can see, I have changed incrementation and changed the type. Let's check it out. As you can see, it's unpredictable result when using int value. So let's move on. Let's save collections. Well, basic collection implementations are not thread safe in order to provide maximum performance in single thread applications. Yeah, of course, we shouldn't use non-thread safe collections in the concurrent context, because using this kind of non-thread safe collections in concurrent context may lead undesired behaviors, undesired results, and data consistency, and so on. We get too many exceptions or errors, syntaxes errors, and so on. So that's why Java collection framework provides factory method to get set safe collections by using synchronized collection, synchronized the name of the collection. As you can see from the slide, we can use synchronized list method to get synchronized set safe list of strings. And also we can get synchronized map by using this method, and we can get thread safe map by using synchronized map. And also in Java util concurrent package, we have newly very well optimized for concurrency and for concurrency environments, new collections. They are very fast. They have very fast, and they are very easy to use. Well, these newly added concurrent collections are categorized into 3 groups based on their thread safety mechanisms. First of all, okay, let's go on. Sorry, guys, for interruptions due to technical problems. So let's move on from, well, newly added concurrent collections are categorized into 3 groups based on their thread safety mechanisms. They're copy on write collections, compare and swap collections, and collections which are using special lock object from a newly added lock framework. Well, copy on write collection, as you know from the name, as you can assume that when it creates immutable array and saves value there, and when value in the array changes, they are creating new array and copying new value there and old values there. So, well, compare and swap collection, it uses compare and swap algorithm, as you know from the atomic operations. And they are concurrent linked queue, concurrent skip list map. And the last one is collections using special lock object for making safety. Yeah. Concurrent hash map, linked blocking queue. Well, for example, in linked blocking queue, they are using 2 different locks for head and for tail. In this case, they are making more optimized linked blocking queue for multi-threaded environment. Well, let's summarize facts about important facts about set-safe collections. Well, most collections in collection API is not thread-safe, and we can get thread-safe collections by using factory method synchronize, a XXX, where instead of XXX, you can use name of collection and you get the synchronized collections. And these synchronized collections are poor at performance in comparison to newly added concurrent collections, because in concurrent collections, newly added concurrent collections are improved for thread safety and performance with different synchronization mechanisms. Well, for example, copy on write, it's read predominant on write operations. For example, in your case, if you're if in your array always almost occurs only read operations, you can use copy on write array list, and so on. Let's move on and take a look to our demo collections, demo to thread safe collections. Here you can see our map, concurrent hash map, newly created, and we have a static class, map pollute thread, which extends from thread class, and we override it run method and in a loop with maximum 10,000. We are creating, generating key value and putting to our map, which is created here. Yeah, it's simple. As you can see, we are creating key value and putting there. And this class extends from thread. Well, in main method, we are creating two threads and we are starting it. And in try block, we are looping it in a loop. We are simply iterating it. Simple iteration, we are doing nothing, simply to catch concurrent exception. Yeah. And we are joining it to wait the completion and simply printing it to our console with map size. Well, as you can see, here we have 10,000 map size. Let's check it out, try to run. As you can see, 20,000, because we have two threads. If we add third thread, it will be 30,000. Well, let's check it with non-thread collection, non-thread safe collection, yeah? Map. All the same, we only change it collection. And here we getting concurrent modification exception. Why? And map size is not expected, because hash map is not thread safe, and using hash map in a concurrency context leads to lost updates, and iterating through them during modification may lead to concurrent modification exception, as you can see from our logs. Yeah, concurrent modification exception. Let's move on. Executor, executor service, executors. Well, all three classes, executor, executor service, executors, are part of executor framework, which provides thread pool facilities to Java applications. What is thread pool? As you can see from the diagram in the slide, thread pool, task queue, task submitters. Well, to understand this diagram, we need to find out what is executor, executors, and so on. Yeah, executor is an object that executes your runnable object, your thread. and it doesn't return any value. Well, executor service is a sub-interface of executor, and it introduces callable interface. In other words, it enhances, it adds more features to executor, and it encapsulates runnable code and returns some value. About callable, we'll talk a bit later. And there we have scheduled executor service. It's also sub-interface of executor service. It also adds some more features to this service. It allows to schedule execution of a callable and runnable tasks. About callable and runnable, we talk a bit later. And executors, it's a utility class for creating executor. Well, from the diagram, you can see we are submit tasks by using executors. Executor have submit method, and we are submit it to task queue. And if in the thread pool we have available thread, it takes this task and it does its job. It executes it. And there we have a couple of types thread pools. So a single threaded pool, fixed thread pool, cached thread pool, scheduled thread pool, and so on. Well, in overall, thread pool, this thread pool reuses previously created threads to execute current tasks and offers a solution to the problem of a thread cycle overhead and resource thrashing. Because all the time creating new threads, it's really expensive. That's why they are using thread pool to reuse already created threads. Let's move on. Also, we have some couple of problems with thread pool. We need to calculate optimal number of threads in thread pool, and it can be calculated by using the number of cores of your processor. And also, another factor, we need to know what kind of tasks we need to do. For example, if we are doing only computational tasks, we can set the optimal number of threads in thread pool, for example, number of cores in your processor or +1. If you have non-computational, for example, getting some network data, reading some files or something else, you need to more deeply calculate thread pool size. Let's move on and check it in demo. Thread pool executors. Short demo. As you can see, here we have my task 1, which implements run number object. We are overriding a run method and simply printing it to the console, yeah? And in the main method, we are creating executor by using executors. It's, as you remember, it's a utility class to creating executor service. We are creating a new fixed thread pool with 4 threads. And in the main method, we are simply executing the newly added tasks, as you can see. Let's start and check it out. As you can see here, here is limit 10, but we have 4 threads. Need to take attention, yeah? We have pool 1, and as you can see, we are printing the name of threads, and we have only 4. For example, if we make it 10 and rerun, we have 10 threads. As you can see, yeah. In this demo, you can see that creating executor by using executors. Also, you can use executors to create executor service. Sorry. Doesn't matter. Ah, sorry, I have another demo. I will show you in another demo. New cached thread pool here in the main method. You can see by using executors and calling new cached thread pool, we are creating executor service. And in executor service, we are invoking all, and we are using callable. And it is a topic in the next slide. Let's move on. Callable and the future. Well, callable interface is similar to the runnable interface. Both of them represents tasks that is intended to be executed concurrently by a separate thread. Callable interface is different from runnable in that the runnable interface's run method doesn't return any value and didn't throw checked exceptions. Callable interface is quite simple. It has one method. It is call. It returns a value, generic v value, and throws checked exceptions. And this generic value v wraps by using future interface. It wraps on this interface. And by using future interface, we get some value which will be available in the future. And here in the slide, you can see some methods of future interface. The first one, for getting value, we have two methods, get without parameters and get with timeout and with time unit. Well, get blocks until result is available. It's blocking operation, yeah? Block until result is available, but no longer than timeout. Also, we can cancel future execution by using cancel method. And also, we can check the status by using isCanceled is done methods. These methods return Boolean value that indicates whether the future is canceled or done. Let's move on and check the demo. As you can see, here we have only a static method, simple method, other task, and simply it prints to console I'm other task. Well, in the main method, we are creating executor service, line 15, by using executors utility class new fixed thread pool with 5 threads. First, we are using runnable, which returns nothing, and we are submitting. As you can see in executor of executor servers, we are using submit method. Well, in comparison to executor, in executor we have execute method. Here by lambda notation, we are passing runnable object, and also here we creating callable object. And here we passing in line 27, passing this callable object to executor by using submit method. And returns future object, generic object, which is type string. Also, we have task 1, but in some kind of lambda. And in try block, first we have other task. And we have future get method with timeout 5, time unit, and seconds. We need to wait 5 seconds to get the result. We are simply printing out, and the last one is other task after future result. So here, our first log must be I'm runnable. The second must be entered callable. And then must be I'm callable task. And then get the future result, yeah? Let's try to run the demo and check it out. Yeah, and here we have I'm runnable task, which is our runnable object, which we pass it to submit method here, I'm runnable task. Second, entered callable. Because we have entered the callable is prints to console. I am callable task. This is not the hello from callable. I'll explain you why. It's here. I am callable task. It's our future task 1. It is the other task. And here we have before future result. I'm the task before future result here. As you remember, here we have this kind of printing. I'm other task, yeah. Here we have I'm other task before future result, and here get the future result. Hello from callable. Our first callable here. Hello from callable. And why it's working like this? Because we are here getting future we are using get method with timeout, yeah, and printing other results. And the last one, I am the other task after future result. It's after future result, and that's all. And also in catch blocks, we have interrupted exception, which can be interrupted, yeah. Execution exception, which can be execution can be in our methods, and timeout exception, which we use it here, timeout. And in finally, we need to shut down the executor manually. Don't forget about it. And there are a couple of ways how to correctly shut down executor. Shut down now, shut down. There are a couple of methods to use for shutting down the executor manually. Let's move on. Thank you for your attention. Then the main part of this presentation is over. Any questions?
Yeah, thank you for your presentation. We have some questions in our chat. Let me read it for you. The first question is, which are better to use, logs or atomic variables?
I couldn't understand. Atomic variables or what?
Or logs.
It depends on your case. Depends on your case. But atomic is really helpful when you have some kind of variable and you need to restrict access to it. Yeah, it really helps in this kind of cases. And when you have a bigger method or class or something like this, you need to use logs, because while using logs, you have more extensive operations. When you can log in the start and unlock in the middle of the method, you can use logs with with the class members.
Okay, yeah, I agree with you that yeah, logs we can use in some methods, and atomic variables it's just when we need to use variable and restrict access to it. And yeah, the second question is how performant are newly added thread safe collections compared to usual collections like HashMap?
Well, newly added concurrent collections, they are optimized for concurrency context. Yeah, in a single threaded environment, you need to use hash map. You don't need to use concurrent hash map in your single threaded operations. They are not they are poor in a single thread in single threaded environments, because they are optimized for multi-threaded environments.
Yes, and yeah, the question was about the performance.
Hash map is highly performance in a single threaded operations, but in a multi-threaded environment, it was to use, because if we use hash map in multi-threaded environment, we get undesirable results. We have inconsistency data, we lost updates.
Yeah. And if we want to use it, we will need to add some other something other to
Synchronizers.
restrict access to it.
Yeah, we need to manually add synchronizers to this hash map. Why you want to add some kind of synchronizers to hash map while you have concurrent hash map?
Yeah, agreed. I don't see any questions in our chat, so I think I hope we answered all questions, and I think we can stop our end our call. Thank you everyone for your attention, and sorry for the technical issues again.
Okay, thank you everyone.
Thank you. Bye.
Goodbye.